Just like linear motion has kinetic energy as 1 over 2 mass times velocity squared, rotation also has kinetic energy, but it comes from spinning. And this rotational kinetic energy is 1 over 2 inertia angular velocity squared. So it's like the rotational equivalent of these linear quantities. Imagine you have a ramp and you place a solid cylinder battery at the top, and this battery has mass m and radius r. You place it at the top of this smooth ramp with a height of h. It rolls down without slipping. What's the speed when it reaches the bottom? Now, before solving, let's assume a few things. We're going to assume that static friction is present, but it does no work because we're just pure rolling. And we're also going to use the conservation of energy. When an object rolls, it moves forward and it spins at the same time. So some of its initial potential energy at the very top turns into kinetic energy, which is forward motion, and some turns into spinning kinetic energy. We calculate how fast it goes by accounting for both. So here's step 1. We have to look at the total energy at the top, and the total energy at the top would be gravitational potential energy. So we can write energy at the top is equal to the formula for gravitational potential energy. How about the energy at the bottom? At the bottom, there's two types of kinetic energy. Translational kinetic energy, which is this linear motion, and rotational kinetic energy, since it's rolling. Translational kinetic energy is given with 1 over 2 mass velocity squared. And as we saw, rotational, the counterpart is this. And because energy is conserved, the energy at the top should be equal to the energy at the bottom. So mgh, which is the energy at the top, equals the energy at the bottom. There we go. So I've just moved this aside because step 2, we have to find the moment of inertia for cylinder shapes because our battery is a cylinder. You can go Google moment of inertia chart and you'll find that for cylinders, the moment of inertia formula is 1 over 2 mass radius squared. And if you don't like Googling stuff, there's a free cheat sheet that I put in the description for free. This battery is rolling without slipping. So the angular velocity is given with v over r. This is the formula. And why did we go ahead and find this? Well, look at this equation that we have here. We're looking for the velocity, but we can't go and solve for that because we don't know inertia. We don't know angular velocity. That's what we're missing. So that's what we've gone and solved here. Anyway, let's go and plug in our values into our conservation equation. So 1 over 2 mass times velocity squared plus 1 over 2. And here's where we plug in our values. Inertia is 1 over 2 mass radius squared. And angular velocity is v over r. And these values are squared as well. Because if you look at the equation, there's a square on the angular velocity value. So we've just gone and taken this equation and we plugged everything in. Now if you simplify this, you get this. 3 over 4 mass velocity squared. Step 4. And here's the final step. All we have to do is rearrange for velocity. Once you're going to do that, you get v equals 4 over 3 gh square root. And let's see, what does this mean for our battery? So if we had real values for the mass and the height of the ramp, we would be able to plug it in here and find the exact velocity when it reaches the bottom. And this formula makes sense because usually if it's just sliding, for example, if you had a box and it was just sliding down, the formula is normally 2gh. Maybe you've seen this somewhere. And this value is bigger than this value. So if it was a plain box, it would slide down faster. Why? Like we were talking about earlier, some of the potential energy becomes rotational kinetic energy. And rotational kinetic energy doesn't directly translate you forward, unlike standard kinetic energy. So rolling objects always move slower than sliding ones with the same starting height because rotational energy steals some of the potential energy. Let me show you a thought experiment, and it's a fun one. It's a race between different shapes. So you have a ramp again, but this time you've got 5 shapes. I'm going to write them out. Here's the 5 shapes. And these shapes are kind of standard shapes you might see in your physics problems that deal with inertia. Why? Because inertia depends on the shape. This is the formula to find their speed. The only thing that changes here is this k. K is the coefficient to inertia. So that means the larger k is, the slower the object is when it reaches the end, because this value becomes smaller and smaller as the denominator gets bigger and bigger. The object that reaches the bottom first is the box. Why? Because the box has no rotational inertia. It's not rotating. It's simply moving. And who comes in last place? It's the thin hoop. The thin hoop has the largest moment of inertia, which means that all the mass is very far from the axis. So the more potential energy that's eaten up by the spin, the less forward motion. And here's one last concept for this video. If you remember all the way back to work and energy, the formula was W equals Fd. There's a rotational equivalent. Because remember, everything from linear motion, they always have some rotational version, right? And here, work done by torque is equal to torque. And instead of displacement, we have angular displacement. Of course, that's measured in radians. What about power? The power formula is W equals work over change in time. This is the rate at which work is done. And it's also equal to force times velocity. The rotational equivalent of this is P equals torque instead of force. And instead of velocity, we have angular velocity. And this is useful because you can find how much energy a motor delivers when turning a wheel, for example. For every topic I cover, I like to create a free cheat sheet. And I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.